they can assemble and bring some new properties at interfaces. So I would like to talk about all these applications, but I will try not to be too long. So our toolbox. So to build stimuli responsive microjets, we need to develop the chemistry. So we basically we prepare some microjets using very classical chemistry, using polyacrylamide or polyacrylates. But this is mainly to drive new systems which are easy to prepare, and then we make physical chemistry, so we aim at understanding their behavior. But then once we have understood their behavior, we want to transfer this knowledge to some systems that could be applied, and especially applied to living systems. And then we need to develop some other types of polymers which are based on biodegradable or biocompatible polymers, and then we target polysaccharides. So for that we need some control process for the polymerization, which can be from the colloidal state, so up to micrometer scales, and then we also can have larger scales like microfluidics to make particles which are below 3 millimeter. And the last thing is that we need to get some functional particles, so we will introduce some various moieties such as ligands to detect some specific signal, especially some biomolecule in the solution. We can also introduce some redox moieties in order to get some electrochemical signal, or fluorophores in order to get some optical signal. Then we also control the structure, as I said, so of course the size, the distribution of the segments, which is really important to control the kinetics of swelling, or the way it will deform. We can also control the internal structure, such as examples which are given here with different core shell structures or capsule-like systems. And we can go to hybrid systems in which we can, for example, load some nanoparticles in that. But if we are interested in encapsulation system, we can load some proteins. So we have worked on that. I won't talk about this today. And we can also load some soft particles, such as droplets. So as an example for encapsulation, I wanted to show you that although those systems are highly hydrophilic, and this is what makes them so biocompatible and biocompatible, we can load some hydrophobic molecules. And especially one generic system is to load oil droplets, and inside the oil droplets you can incorporate some hydrophobic drug, for example. So here we developed a system in which we loaded progesterone, and the idea was to degrade the matrix by using an enzyme. So we, as a polymer, we used hyaluronic acid, which is a well-known biocompatible component, which is produced by bacteria. And this hyaluronic acid is present in the external membrane of the cells, and it is degraded by an enzyme which is present in vivo and which is hyaluronidase. And so in these systems, if we degrade the matrix, we can deliver very small droplets that can then diffuse inside the body, and that will carry the drug. And we prepared, as you can see here, we prepared the particles, which were nicely monodispersed. They had this slug shape, and we could load, so the particles were about 100 nanometers. So the microjets were 200 micrometers, but the inner oil droplets were about 100 nanometers. And they can diffuse easily with Brownian motion. So what we've done is when we introduce the hyaluronidase, you can see here that the matrix is degraded and it works like a tablet, and it will dissolve, and instead of having gas bubbles that escape, here you can see that the oil droplets are diffusing in the body, and so they can go and join the circulation. So you can imagine to get an implant, a subcutaneous implant of this system that can deliver the drug. And you can see that the kinetics here is triggered by the amount of hyaluronidase which is present. Okay. So this is just a first example. As a second example of what we can do with those responsive microgels, we try to amplify the signal. So which type of signal? So mainly fluorescent signal can be something that is interesting because these systems are small. So in this case, particles which are below the micrometers, they can enter into cells, and if you can change the fluorescent signal by a stimulus that is present inside the cell, you can detect this stimulus intracellularly. And so we have developed some particles that are fluorescent and that can be sensitive to sugar, so glucose, fructose. So how can we do that? We modified the particles with a compound which is boronic acid, which is a ligand for diols. And in this case, the sugar will make a cyclic ester with the boronic acid, and it will induce the swelling of the particle. And at the same time, we functionalize the particles with the fluorophore, and the fluorophore here will be a complex of ruthenium. And so here are an example of the particles that we have developed, and they are sensitive here to fructose, and at the same time you can see that the fluorescence will decrease as a function of fructose concentration. So how is it possible? So here you can see that there is a change in the intensity of fluorescence and as well as a change of the maximum wavelengths. And this is because when you change the swelling of the particles, you can change the distance between the fluorophores, and you can change the local environment of the fluorophore itself, and this can induce some change of the quantum yield and also of the lifetime. And here, we change the distance between the fingering of the boronic acid and the fluorophore, and this is responsible for this change. We also developed a collaboration in our group. There are many electrochemists, and especially Nisho Sojik, who is a specialist about luminescence. So this is a luminescence which is not generated photochemically but electrochemically. That means that you apply a potential, you change the state of a redox compound. So in this case, the ruthenium complex, which goes from the form 2+ to 3+, and then through the addition of another reactant, which is also another redox species, which is sacrificial, there will be an emission of light. So I don't enter into the details because this system is quite complex, but just to show you that those microgels can also work as electrochemical sensors combined with light. And when we started this project, we thought that we would have a turn off the luminescence, because generally when the microgel collapses, it will block the diffusion of the reactant. But here the ruthenium compound is chemically bound to the chain, so we also change the distance between the ruthenium compound. And in fact, it turned out that instead of a decrease of the signal, we got an increase of the signal. So as you can see here we apply the potential, and at 1.2 you have the potential of the ruthenium complex, and at the same time you can detect some emission of light, and the emission of light was enhanced at a temperature where the particle were collapsed. So, and we showed that these enhancements was really directed by the volume phase transition of the particles. So this is something intriguing, and we found out that in fact this system is kind of schizophrenic, because on one side the microgel really blocked the diffusion. We could verify by making those hydrogel films that the current that goes through the film is smaller, but in spite of this, there was an enhancement of the luminescence. So the luminescence comes from the new pathways that the microgels can offer to electrons, because the ruthenium complex come close together. So after this, the last part of my talk, and I'll try to move fast, is it fine? Is that you can also use responsive microgels as additives for formulations. And we were interested in this system because these particles, they can deform, but some of them, they can also adsorb at interfaces. And normally, when particles adsorb at interfaces, they can make a dense packing like this, but more than that, in fact, those particles, because they are soft, they can deform. And in particular, they can flatten. And you can see on this series of images, this is a series of images that were taken from AFM pictures, where we could take a substrate through the interface and then collect the particles at the interface. And you can see that depending on the time of adsorption, the particle can pack more or less densely. So at low time scale, they don't have to, so they are not numerous enough, so the concentration is low and they have enough space to flatten. So they will make a regular array of hexagonal compact particles, but which are deformed there. And after time is going by, they can pack more or less densely, and their shape is deformed, as you can see here on the profile section that is on the right side. So you can really change the packing from flattened particles to compressed particles. So this is something that is tunable, and that could be interesting for formulations, and in particular in formulation, if they can go to the interface, to a liquid interface. If you put oil in contact with water, so the particles remain dispersed in the water phase because they like to be swollen, water swollen, but in spite of this, they can also go to the interface, and they can stabilize some emulsions if you disperse the oil in the aqueous phase. And these emulsions are stable for months at rest, at room temperature, for example, if the particles are swollen at room temperature. But in the case of particles which are thermoresponsive, when you heat these particles above their volume phase transition, they can, so the emulsion will be destabilized on demand. So this is interesting for formulation issues. And so maybe I will skip this. And what is also interesting in such particles is that because you can tune their deformation, we could show that depending on the pathway where we prepared the emulsion, we could control the way they order at interface, and there is a real link. So believe me, we have made many experiments for that, and we have shown that there is a systematic relation between the way they pack and the properties of the resulting emulsions. And for example, here you have emulsions where which cannot flow and which can be as a solid, which can behave as a solid, and in the other case, the emulsion can flow. So there is a real way to tune the properties of the emulsions, but this can be also applied to foams. because these systems are kinetically trapped, so you can change the conformation and they behave like proteins at interfaces. So it also helps us to understand how protein behaves at interfaces. And through these assemblies, we can go towards more sophisticated materials that for encapsulations, and for example, we can make colloidosomes out of that. And also we can imagine many types of hierarchical systems. Okay, so with that, I want to thank, because I'm almost old, so I went through various projects over the years, so many collaborators and students, and so I would like also to thank you very much for your attention.